All right, let's get started. Excuse me for being a couple minutes late. So today we'll talk some more about momentum, collisions, and a new concept, center of mass, which is going to be very helpful in decomposing complex motion into two simple parts. Okay, before we get started, are there any questions, issues, concerns? Deep philosophical physics questions you came up with in a dream?
How are you?
How am I? That's not a deep question. No? All right.
Okay, so
Okay, a
I
question.
have a deep philosophical question.
All right.
At the most fundamental level of the universe, is everything particles, fields, or a combination of the two, or something we don't know of?
I guarantee you the answer is it's something we don't know. But the question is, what is the universe made up at the most fundamental level? We really don't know the answer to that. But your question says, is it particles or fields or something else? Something you have to understand is that particles are not disconnected from fields. Particles are just excitations of fields. So a particle is just when there's energy in a field and it gets excited above its ground state, that's what a particle is. So you can't have particles without fields. What is the universe at its most fundamental level? Currently the best idea is little vibrating strings. So maybe you've heard of string theory. Problem is that string theory is currently mathematically pretty and fascinating, but it makes no testable predictions. So it's like you could equivalently say the universe is a bunch of tiny elephants, but you can't tell. Okay, nice theory, but how do I know if it's true, right? So a theory has to be falsifiable before it's a scientific theory, and string theory is not yet falsifiable. So it's a mathematical playground up to this point. So we don't know. Okay, wow, so actually a good philosophical question, thank you. Okay, so we are talking about something much more concrete than tiny elephants. We're talking about momentum and collisions, right? Okay, and we define momentum, right? Product of mass and velocity. And we noticed that we connect this to another basic equation we use all the time, right? By recognizing that a change in momentum is equivalent to a force, right? That's what a force does, is that it changes the momentum of particles or objects, okay? And we use this momentum, the concept of momentum, to think about collisions, right? Because if there's no external force on something, that means there's no change in momentum. That means that there's conservation of momentum, right? P initial equals P final. And we use this to great power to understand what happens in collisions, because the initial total momentum is equal to the final total momentum, right? We also, so this is for momentum. We also were able to use the concept of conservation of energy, but this is only in the case of an elastic collision. Right? So we have conservation of kinetic energy. So you have KE initial equals KE final, right? So that was very helpful. Okay, and let's just warm ourselves up by doing an example of a collision. Get back into practice of using these equations, since last week was a long time ago. All right, you guys probably did like 5 problem sets for 5 different classes since then. So say we have particle A. Particle B is initially at rest. So VB initial equals 0. VA initial is 4 meters per second. Okay. A is incident upon B, and afterwards A flies off at some angle alpha. Oops. A flies off some angle alpha. Right? And B flies off some other angle beta. And we're given, what else are we given? Okay. Final velocity of A is 2 meters per second. Okay, and the question is, what is the final velocity of B? Well, let's start thinking about it in terms of energy. Right? If it's an elastic collision, which it looks like it is, why do I suspect it's an elastic collision? So they don't stick together, they don't change shape, right? They bounce off each other as if their interaction was dictated by a couple of springs, right? Where you store the kinetic energy and potential energy and then release it back into kinetic energy, not having lost any of it. Okay, so we say the initial kinetic energy is equal to the final kinetic energy, right? Initial kinetic energy is just 1/2 ma VAI squared, right? Just the kinetic energy of particle A, there's nothing in particle B. And the final kinetic energy is VB F squared plus 1/2 ma VAF squared, right? And we know this already. We know this. We are given the masses. This one is 0.5 kilograms. This one is 0.3 kilograms. Yep. Okay, so we know, in this equation we know everything except for what VBF is. So the halves cancel, right? And we have VBF squared is MA VAI squared minus VAF squared, right, divided by MB. Did I get that right? That's right. This is going to be larger than this, right? So this is a positive number, which is good because it's squared, and it's related by the ratio of masses. Does this ratio make sense? Well, the velocity B is proportional to the mass ratio of A to B. So if A is much, much heavier than B, imagine a bowling ball hitting a ping pong ball, then B's velocity is going to be large. That seems about right. If A is really small compared to B, imagine a ping pong ball hitting a bowling ball. Bowling ball is hardly going to move, so I think this ratio makes sense. Okay? So we can solve for this one, given these numbers. VBF is, what did I get? 4.5 meters per second. Okay, that tells us the magnitude of the velocity, right? Energy is a scalar. We get one equation, we get the total magnitude of the velocity. Because what I really was able to get was VBF squared. Take the root of it, you get the magnitude of the velocity, you don't get the direction. Energy doesn't have directional information because the equation is just one equation, it's a scalar. To get the directional information, you have to apply also conservation of momentum, right? And in this case, we have two equations, because remember, momentum is conserved separately in x and y. It's two separate conservation laws, okay? So we have MAVAI x component here, is MAVA final x plus MB VB final x. And then the y component, the initial state is going to be 0, right? Because there's no momentum in y initially, is MA VAF y plus MB, that's a B, and that's supposed to be a V, VBF y. Okay? So here I know the masses, I know A's initial velocity, I know the magnitude of the final velocity of A, right? I don't know the angle, alpha. So how many equations do I have? I have two equations here, right? And how many unknowns do I have? It looks like I have 1, 2, 3, 4, right? So what do I do? Sorry? Trigonometry, right? Because saying I don't know VAFX and I don't know VAFY is not really true. I know something about them. I know that their sum in quadrature is equal to the final velocity, which is 2 meters per second. So I can relate them to each other, right? I have a constraint relating these two and a constraint relating these two. So I can express these guys as components of the velocity vector, right? So I can say MAVAIX is MA, and here I write VAF cosine alpha, right? MB VF cosine beta, right? And then I have something similar for y, except I write MA VAF sine alpha plus MB VBF sine beta. And now I have two equations and two unknowns, and I can solve it. Questions? Okay, that was just warm up to remind us what we learned last week. And that's useful for thinking about a couple of particles, right? One thing hitting another thing. Now I want to talk about systems of particles, because we're going to extrapolate from two particles to systems of particles to real objects that have real funny shapes. Right, they can't be just described as point particles. Okay, so imagine you have not just two particles, but you have a whole system, right? Some n particles, each with their own velocity and their own mass. Right? Maybe you shot a shotgun or something, and each shot is coming out, and they all have slightly different velocities, slightly different directions, slightly different masses. Okay, what can we say about this? Well, we can say that the momentum of the whole system is the sum of the momentum of each thing, right? MI VI, right? So this is M1 V1 plus M2 V2 plus etc. Right? We can say, well, the momentum sums linearly, so we can add them all up. And this is not just one equation, remember. This is, these are vectors, right? So these are three equations if we're working in 3 dimensions. Okay, so that's the momentum of the whole thing, right? Now, what about the momentum of the center of mass? Right, somewhere here, there's a center of mass. And remember last time we talked about external forces and internal forces. If you draw a circle around this whole system of particles, right, and say, this is my system. Now, in this model, there's no air resistance, there are no forces on this system, and so there's going to be no change in momentum for this whole system, right? So this quantity is going to be constant, right? And that means that there's going to be, that while they may move around relative to each other, there's going to be nothing that affects the whole system. So this momentum is going to be constant. And so we can think of a concept of the center of mass. We can say, somewhere in here, there's a point that we can use if we're outside the system to think about the whole system as if it was concentrated at this point. Okay, because if I'm outside the system and I'm going to perform an action on the whole system, I don't necessarily care about the details of what's going on inside. In fact, it'd be a lot easier for me if I could just treat the whole system as a point particle with some mass and some velocity. So we're going to create this concept called center of mass, which is like an effective particle. Okay, I want to find an effective particle. What is its mass and velocity so I can treat the whole system as if it was just that particle. Okay, so how do I do that? Well, first thing I can do is define the momentum of the center of mass. And I say, well, momentum of the center of mass is just the momentum of the whole system. Done. What about the velocity of the center of mass? Well, if I have the mass of the whole system times the velocity of the center of mass, right, this should be equal to the momentum of the system. Right? Momentum is mass times velocity. Okay? What's m? M is just the sum of the masses. Right? So this is m1 plus m2 plus m3, right, times VCM, right? Okay, so that lets me say what VCM is. V, the velocity of the center of mass, is m1v1 plus m2v2 plus divided by m1 plus m2 plus, right? So I can define the velocity of my effective particle, my center of mass. This is a theoretical idea, right? It doesn't have to necessarily be anything at that point, as the mass-weighted average of the velocities. See? I'm basically just averaging the velocities, but I'm weighting them by their masses. So things that have a lot of mass give more weight in the average than things that have almost no mass. So it's a mass-weighted average of the velocities. That's what the meaning is of the velocity of the center of mass. Okay, and now if I want to know where it is, I can do a similar thing with the position. I can do a mass-weighted average of the positions. How did I do that? Did I just say, well, look at the structure of it, and we postulate what it might look like? Sure, that's a good hand-wavy argument. Is there a more rigorous mathematical way to derive what this must be? Well, what's the relationship between velocity and position?
Velocity derivative is position.
Yeah, so what do you get if you take the derivative of this? Well, you just differentiate everything with respect to time. All the v's turn into r's. So if you can establish the momentum of the center of mass, then it's easy to establish what the velocity of the center of mass is, and therefore what the position is. Okay, so what does this mean? Right, what are we talking about when we mean the center of mass? Well, let's think about some concrete examples. Right, now in the case of this particular blob of shotgun pellets, it means that I can think about the motion of each shotgun pellet in two terms. One, I can think about the motion of the center of mass, which would be very simple. There are no external forces on it, so it's just a particle flying through the air, right? It got an initial kick from the shotgun, and now it's just flying through the air. I can use simple projectile motion to model it, right? Very simple. And then I can think about the motion of each particle with respect to the center of mass, right? So every particle inside the swarm, it can be described as the motion of the center of mass plus its motion relative to the center of mass. And usually, those two problems are both fairly simple. Okay? So, but let's get back to concepts of the center of mass. Say, for example, you have some sort of homogeneous object. Okay? Cube. Where is this going to be its center of mass? Well, the center of mass is the mass-weighted average location. Right? So here, we can't really do a sum, we have to do an integral. Right? Because this object is composed of 1,000 or 1,000,000 or infinite number of infinitesimal tiny bits of mass. But by symmetry, it has to be at its geometric center. Right? There's no other possible answer. So an object which is homogeneous, the center of mass is just going to be at its geometric center. Right? So you have a sphere, center of mass is going to be at its center. If you have a cylinder, right, center of mass is going to be at its center. If you have a disk, right, very thin disk, or a sloppy pancake, center mass is going to be at its center, right? What about this? What if you have a thin donut? Where's the center of mass? At the center, right? There's not necessarily any mass at the center of mass. Okay, it's the geometric, it's the mass-weighted average of all the stuff. It can average out to some place where there is no actual mass, just like in this case, right? Dispersed set of shotgun pellets, there's not necessarily anything at the center of mass. Okay? Now the center of mass is a sum, right, or an integral. That's nice because it means if you want to calculate the center of mass of a complicated object, say for example, this is the example they have in the book, you have a water molecule. And you're like, geez, how do I do the center of mass of some weird shape like that? Well, you could do it rigorously and say, well, I'm going to have a function r, which and a density function and do an actual, three-dimensional integral, but boy, that sounds like a pain, especially because how are you going to define this thing, the shape of this thing? It can be a mess. Well, because the center of mass is like a sum, right, then these things just add linearly. So, for example, this is oxygen, H1, this is your second hydrogen. Then the center of mass of this guy is just the position of the first hydrogen times its mass, plus the position of the second hydrogen times its mass, plus the position of the oxygen times its mass, divided by the sum of their masses. So if you can find the center of mass if you can break down a complex object into simpler objects and find their centers of mass, right, here, here, and here, then you can use those centers of mass to build the center of mass of the more complex object. And that's because the center of mass is just a weighted average. So you can just always add more stuff to your average. Okay? So I told you that center of mass was a useful concept for thinking about the motion of complicated things. Let's be a little more concrete about what I mean by that, right? Say you have a rocket, okay? And your rocket has two stages in it. Maybe there's a person in this stage, right? And this stage is just fuel, okay? You launch this thing up, and we're not going to do any complicated rocket dynamics. We'll say it just gets one initial boost. So there's a slingshot here or something that shoots your rocket up into space. Okay? And now it starts moving as a projectile, right? So no forces on it other than gravity. It has initial velocity. So it just moves like a projectile, right? Okay, easy problem, right? What if halfway through its flight, these two guys explode with a little explosive charge to separate? Okay, so at this point here, one guy goes up, the other guy goes down, right? So now you have a more complicated trajectory. Like, yikes, that sounds like a nightmare to calculate kinematically, right? And you're flying through the air, you get this little kick. How do you calculate this trajectory? It's sort of a mess. Well, it turns out you can separate these two problems into two problems. Separate this one complicated problem into two problems. Say, well, there's no external force on the rocket. There's an internal force, right? It's separating into two pieces. This is just like the skaters who are spinning on the ice, pushing and pulling each other. There's no external force on the rocket, which means the motion of a center of mass is not going to be affected by anything that happens internally. So no external forces means, other than gravity, right? It means no change in its force other than gravity. So the motion of the center of mass is going to be just like projectile. Right? Even though there's no longer anything at the center of mass, the motion of the center of the mass of these two objects is going to move in a simple trajectory. So to understand the motion of one of the pieces, you only have to understand the motion of the center of mass, and then understand the motion of this guy relative to the center of mass. So for example, if you're told that at this point here, it gets an initial velocity up of 1 meters per second, and the other one gets an initial velocity down of 1 meters per second, then you just need to think about the motion at 1 meter per second relative to the center of mass, right? So the motion is the motion of the center of mass plus the motion relative to the center of mass. This is a classic trick in physics to take a complicated problem and to break it up into similar pieces, all of which you can handle. Right? If you say, well, all I have is a hammer, let me see if I can turn this problem into just a bunch of nails. Right? Questions about that? Okay, let's do a clicker problem. So yeah, here's the same diagram I was just drawing, but with a more accurate depiction. You see that the trajectory of each piece looks rather complicated, but remember that it's just the trajectory of the center of mass plus the trajectory with respect to the center of mass, both of which are fairly simple problems. Okay, so let's get back to our favorite example. our pirate ship. Okay. Let's just do a very silly question first. All right. Fires a cannonball with no air resistance. The trajectory depends on what? All right. Talk about it with your neighbor. Argue about it. Vote again.
Are you assuming that the camera motion is the same force? It doesn't matter because I know, and then with the adds.
I think you have the information you need. Okay, everybody vote again. Talk about it with your neighbor. Okay, looks like the A's are winning. Hey, who believes the answer is C and wants to argue for it? Yes, gentlemen, share your discussion with us. Hello. Notice you're the only one in the room talking?
Well, first we were talking about whether the mass matters or not. Well, B we obviously don't know it, but we were talking about whether mass matters or not, and then we put into consideration the force that the cannonball, the cannon was shooting the cannonball with.
Mm-hmm.
But then we realized that that information is already contained in the initial velocity. So technically it would be C and A, but we just went with A for simplicity.
Okay. Anybody else? Okay, so the answer is A, right? It's a kinematics problem. It's determined by the initial velocity. Okay. What about if the cannonball is spinning? No pressure, no air resistance. What if the cannonball is spinning?
Oh, the cannon.
Cannon is spinning.
What if the universe is spinning, man? These are not supposed to be trick questions. You guys are paranoid. All right. So, does it spin matter? Why not? Momentum's conserved, so what?
So it doesn't matter whether it's spinning because the angular momentum or the linear momentum is not going to depend on whether it's spinning or not. So the velocity is the same, and it's going to be the same.
We're interested in the motion of the center of mass, right? The center of mass change when it spins? No. Does it matter if there's even anything inside it pushing it and pulling it? Doesn't really matter what's going on inside it, right? We only care about the motion of the center of mass in this case. So the fact that it's spinning is irrelevant, right? What if instead of firing a spherical cannonball, it fires a piano? And this piano is spinning. Now does it matter? I know you want to see a cannon that can fire a spinning piano, right? Okay. Some people believe in the piano-ness. Okay, the point I'm trying to make here, is that we're only interested in the motion of the center of mass. Anything that's going on inside the system is irrelevant, right? Whether the cannonball has a little bit of warmth, whether the molecules are vibrating inside it, whether there are animals stowing away inside the cannonball, none of that matters. As long as we know the initial velocity, we can treat it as a single particle and just calculate its trajectory, regardless of whether it's a spinning colored piano or not. Okay? Let's think a little bit more about what this means, this concept of center of mass, right? It's really useful in solving a lot of kind of problems. Okay? So let's say we have two friends. Okay? Here's, this guy's name is Ramon. And Ramon is 60 kilograms heavy. Okay? And over here is his friend James. And James is 90 kilograms. Okay? And James is at -10. Here's 0. Here's 10. Okay? Here's James. Okay, now somebody puts a beer here. Okay? Frothy beer here. And gives these two guys a rope. Okay, connecting them. And they're standing on a frictionless surface like ice. Okay? Now the question is, if they're both pulling on the rope, who gets to the beer first? Ramon. Why? Because he's lower mass. Okay, well let's think about that. What is the center of the mass of the James-Ramon system? Right? Is it at the beer? No, because they don't have equal masses, right? So let's calculate it. Well, the position of the center of mass is a mass-weighted average of the positions, right? So it's 90 kilograms times -10 meters plus 60 kilograms times plus 10 meters divided by the sum of their masses, right? And I get -2 meters. So the center of mass is right here. Okay, that makes sense. It's more weighted towards James. He's heavier, right? So let's think about what happens as they pull on the rope. Now, are there any external forces? No. Is the center of mass going to change? No. So we can use that to analyze this. Let's say, for example, what happens when James gets to -4 meters? Okay? Where is Ramon? Well, put in -4 meters here. 60 kilograms times x Ramon over 90 plus 60, right, equals -2. The center of mass is not going to change. So I can say for any position that James gets to, like for example, I just chose -4 arbitrarily, I can figure out where Ramon would be, right? And it turns out in this case is 1 meter. Okay, so if James goes 6 meters, Ramon goes 9 meters. Right? In order to keep the center of mass in the same position, they have to move different distances. And you notice the ratio there, 6 to 9 is exactly the inverse ratio of their masses, right? Okay, so is it possible for James to ever get to the beer? Yes? Well, let's see. It's a one-dimensional ice flow,
So they
right?
can't jump?
Is Ramon gonna leave it alone?
So let's see, all right? Let's try.
Either way,
We know Ramon's position at any point for James's position, right? So if we say the center of mass is unchanged, right? And we say he's at 90, he's at 0, right? If James gets to the beer times x Ramon, right? If he's going to be at 0, where does Ramon have to be? Well, we need a negative number, right? So in order for James to get to the beer, Ramon has to pass through James, which means he already got to the beer. Right? They basically have to switch positions for Ramon to ever get there. Right? So James has got to trust Ramon to leave him some beer because he's definitely going to pass through it on the way. See, so the concept here of center of mass makes this problem very, very simple, whereas otherwise it would be quite complicated. You have two forces, right? A complicated system. But the motion of the center of mass is really quite simple. Okay? Now, does it matter, for example, how hard either of them pull? Does it matter if one of them doesn't pull at all? No, it doesn't matter, right? Ramon could just stand there holding the rope, knowing that no matter what John does, Because all he can do is pull, he's getting to the beer first. Right? Hence the power of the center of mass. What's that?
It's kind of hard to visualize because it's frictionless, and when you pull on a rope, you imagine your feet planted.
Right, but if you pull on a rope and your feet are standing on ice, then you're going to slide.
Yeah.
Right? Okay. Let's do another example problem. All right, questions about that? No? Okay. Okay, here we have a yellow block and a red rod are joined together. Each object is of uniform density. The center mass of the combined object is here. Okay? The question is, which of these two guys, this one's yellow, this one's red, which one has the greater mass? You think they have the same mass? What do you think about it?
What's the length? What's the length of
I think that these are drawn to scale, so the red one is longer than the yellow one. But they're of uniform density. Well, how do we figure it out? Where is the center of mass of the yellow system? Where is the center of mass of the red? Here, right? Okay, so if the center of mass, call this 0, right? If the center of mass is 0, now we can just use the centers of mass, right? X yellow, M yellow, plus X red, M red, right? Then M yellow is negative X red over XY times M red. Did I get that right? Yep. Okay, so obviously X red and XY have different signs because they're on the opposite sides of 0, right? But and X red, we know, is magnitude of X red is greater than the magnitude of X yellow. Does everybody agree with that? All right? So that means what? The yellow is more massive than the red, right? Why is that? Well, to balance out the red, it has to have more mass because it doesn't have as much distance. Right? The center of mass is this product. Either you're far away and light, or you're close by and heavy. Right? So for these things to have a center of mass which is exactly at their interface, means that this sum has to balance. Right? So a particle, a contribution that's really far away makes a greater contribution than one that's closer.
If the red wasn't attached directly to the center, the center, horizontal center line of the yellow block would become a two-dimensional problem.
If the red wasn't attached, you mean there's a gap here?
No,
If it was shifted down or
Yeah,
up.
if it was shifted down or up.
From the center of
Okay, if it's shifted down enough, well, yes, but you can calculate each dimension separately, right? So yeah, if this thing was down here, for example,
Yeah.
then where would be the center of mass in 2 dimensions? Well, in X, it would be along this line, right? Because the X argument still holds, and then the Y argument would be somewhere, between the 2 centers of masses of Y. Okay? Other questions? Comments? Okay. Let's do another one of these problems. Here's one from the book. It says a 45 kilogram woman stands up in a 60 kilogram canoe, which is 5 meters long. Okay, so here we have the canoe. A woman. So her mass is 45 kilograms. The canoe is 60 kilograms. And the whole canoe is 5 meters long. Okay. She walks from a point 1 meter from one end, so here, this is 1 meter, to a point 1 meter from the other end, so 3 meters. If you ignore resistance to the motion of the canoe in the water, how far does the canoe move during this process? So she walks along the canoe, and we were told there's no resistance to the motion of the canoe. So obviously this is a center of mass problem. Right? The center of mass of the canoe is not going to change. The question is, how far does the canoe move? So how do we figure this one out?
You assign a center of mass before, after, and then it's the same.
Yeah, so the center of mass doesn't change, right? And what do we need to know to calculate the center of mass? Well, we need to define an axis, right? So we call this x plus x. And let's say we put 0 here, I guess. So the center of mass initially is the mass of the woman times her position, -3/2 meters. Is that right? Plus the mass of the canoe times its position, 0. Right? Now, is the canoe a particle? No. So really what I should do is sum over all the particles, but I can replace that here with just the center of mass of the canoe, right? Here, notice I'm treating the canoe as if it was a particle at its center of mass. That's the power of this kind of approach, is you can simplify a complex structure into just a point. Okay, and this we know, right? This is just a number. Now the center of mass at the end is 3/2, right? Plus 3/2, plus the mass of the canoe times x of the canoe, right? So if we want to know where the canoe is at the end, we just set these two things equal. The only thing we don't know is x canoe. Questions? Okay, good. Okay, let's see. Okay, let's do the asteroid problem. Okay, here's more of a proof sort of a problem than we typically have. This one says 2 asteroids with masses MA and MB. All right, so asteroid MA, this one has MA, MB. 2 asteroids with masses MA and MB are moving with velocities VA and VB with respect to an astronomer in a spaceship. Okay, so here's our spaceship. All right, we have an astronomer inside. Okay, and they're moving with velocities VA and VB with respect to the ship. Okay, so we'll say that's VA and VB with respect to the ship. Okay. Now the problem says that we want to show that the kinetic energy of the asteroids can be written as the sum of their mass times the velocity of their center of mass squared. Okay, so here we're arguing that the kinetic energy of this guy can be found just if you know the velocity of the center of mass and the sum of their mass. Okay, so we're extending this concept of center of mass into kinetic energy from momentum and position. Okay, and this is just right. Okay, where excuse me. Right, yes, good. Okay, where V prime A, V prime B are with respect to the center of mass. Okay? So the kinetic energy of the pair of asteroids is the kinetic energy of the center of mass plus the kinetic energy of their velocity with respect to the center of mass. See, so we've broken up the concept of kinetic energy into kinetic energy at the center of mass plus kinetic energy with respect to the center of mass. Just like earlier when we were talking about the flight of the two parts of the rocket, we broke it up into trajectory of the center of mass and trajectory with respect to the center of mass. Okay, so these guys here are velocities with respect to the center of mass. If these two guys were joined together into a single asteroid and had no velocity with respect to the center of mass, these guys would be zero, and this would reduce to the standard kinetic energy terms we expect, right? Okay, so we're given these velocities, and we need to calculate it in terms of those velocities. Okay, so that's the statement of the problem. Okay, the first thing to do is just to relate these guys and say, well, the velocity of asteroid A is the velocity of the center of mass plus its velocity with respect to the center of mass. Right? This is just a brain translation. The velocity of asteroid A with respect to the ship is the velocity of the center of mass with respect to the ship plus velocity of A with respect to its center of mass. Similar for B. Right? Okay, and once we've broken this up, we can go on to think about what V squared is. And remember that these guys are vectors, right? V squared A is V prime A squared plus VCM squared plus 2 VA dot VCM, right? And this one similarly, VB squared is VB prime squared plus VCM squared plus 2 VB dot VCM, right? So all I've done is express the velocities relative to each other and then expand that out to get my V squared terms, right? Now if I want to start with that guy, right? I want to end up with that. So if I write the kinetic energy in terms of the total kinetic energy of the system, I can just write initially as MAVA squared plus 1/2 MBVB squared, right? Just the mass times the velocity. But what I want to do is express it in terms of the velocities of the center of mass and with respect to the center of mass. So that's why I calculated these guys here, so I can now plug them in here and get a new expression, which I hope I can be able to simplify to that expression, which is our target. Okay, so if I plug that in here, I get 1/2 MAVA prime squared plus 1/2 MAVCM squared plus MAVA dot VCM, right? That's the first part of it, where this 2, the 1/2 cancels with the 2 there, so you don't have a constant in front of that one. And then a similar expression for B, right? Right, exactly the same expression, but for B. Okay. All right, so now what I can do is I can start to gather some of these terms together. All right, like I have a term for the center of mass velocity. So I can say this is 1/2 ma plus nb times vcm squared, right? That takes care of this term plus the b equivalent term. And then I have a term that's like the individual velocities with respect to the center of mass. So ma v prime squared a plus mb vb prime squared, right? That's just this term plus the equivalent one for b, right? Plus the leftover stuff, ma va plus mb vb dotted with vcm, right? And so now what can I do? Well, this one here is just m, right? So it's looking pretty good. I've got the first term, I've got the second term, and then I've got this term. What can I say about this one? Anybody?
It's 0 because the angle between the velocity of the center of mass and the velocity of each object is 0.
The angle between the velocity of the center of mass and the velocity of each object is 0. Why is that?
Because they're all going in the same direction.
Not necessarily, right? There could be an opening angle between the two. You're assuming that they're moving in parallel, right? Well, what are these velocities here? These are with respect to the ship, right? And this is the velocity of the center of mass, again with respect to the ship, right?
If they're dotted, it equals 0 since whatever's happening within the system, so the center of mass are going to be the same relative to each other. So your dot product would just be 0, so it just cancels.
All right, so explain that again.
Because the objects are with respect to the ship, and then the center of mass is the system with the ship and the asteroids. When you dot them together, you're going to have 0.
The center of mass refers to just the 2 asteroids, right? The ship is just an observational reference point. I don't think that changes your argument. Keep going.
Basically, the dot product equals 0 because your velocity of the 2 asteroids and the velocity of the center of mass are the same because since the 2 asteroids are within the system, it's moving the same relative to the system itself.
So you're saying the velocity, these guys are the same as this one?
Not the same, but when you dot them, they get the same thing. So they get the opposite, so the dot product equals 0.
I think I kind of get it. So I think the velocities of your 2 asteroids are going to be components of the velocity of the center of mass.
Mm-hmm. This is the momentum of the center. This is the momentum of the center of mass, right?
Yeah.
MAVA plus MVVB, yeah. And so?
mean, so, well.
All right, keep thinking about it. We're making progress.
If you divide by the sum of the, like, to get the average, what we did earlier, where you do the mass times the velocity of one. I mean, the thing is that the vector addition of the two velocities is going to be the same direction, even though the magnitude won't be the same. It's going to be the same direction as the other one, as the center mass, because the I'm not very eloquent today, but if you divided the MAVA plus MBVB by MA plus MB, wouldn't that give you the velocity of the center of mass?
It would give you the velocity of the center of mass, yes.
So you got rid of some scalars, but you still have the same vectors. So when you dot the vector, it's going to equal 0. Right? Maybe.
By that argument, yes. Anybody else? You had something to say?
I was going to ask, since VA and VB is a component of VDCM.
Component, what do you mean by components?
Like, they add up to, if you add them up, they should have the same direction as the velocity of the center of mass.
Well, not necessarily, because the velocity of the center of mass is a mass-weighted average, right? It's not like VCM is VA plus VB, right? It's mass-weighted average. So the direction of the center of mass with respect to either asteroids depends on the relative masses, which isn't given. It just says MA and B.
Well, so wouldn't that mean that the momentums are components of the momentum of the center of mass?
Yes.
Because that does take the mass into account.
Exactly. And so?
You would add the momentums together to get the momentum of the center of mass?
Yes, which is exactly what we have here, right?
Yeah.
Momentum of the center of mass, right? And so? Okay, I'll let you guys off the hook. The answer is that when I did this calculation, what should this one be here? This one should have a prime, right? Right? Which means these guys have primes, right? And so now what is this quantity here? This is the momentum of the center of mass with respect to the center of mass. What's that? 0 by construction, right? So that's the answer. Okay, so this is just a way to decompose the kinetic energy into the various pieces and to show you that you can construct the center of mass, the kinetic energy of the system as the kinetic energy of the center of mass plus these other pieces. And if you break it down and do all the math and do it correctly, you see that all the complicated terms vanish, right? So I wanted you guys to think about that because I wanted to see you guys cogitate about what you can conclude about the center of mass. But in the end, I mean, if this had been without primes, then it would not be trivial to say 0 because it would be the velocity with respect to the ship, which is not necessarily 0, dotted with the velocity of the center of mass, which is not the same direction or not necessarily 0. So certainly it was not easy to draw. Right? But I like watching you guys think about it. Thank you for your ideas there. Okay, questions about that? Make sense? Okay. There's time for one more example. Okay. You guys want to do an easy one or a hard one?
Hard.
Yeah.
Hard.
Hard? Anybody prefer easy? Okay. All right. Let's do a hard one. Okay. don't know if you guys have ever done algebra at a board, but it's a totally different experience than doing algebra on a piece of paper in front of you. It's much harder to spot your mistakes when you're looking at a huge sheet of paper right in front of you than when you're sitting down at a desk. I almost always make algebra mistakes at the board. Like when I was in grad school, I broke my wrist like a week before finals, and I had to take every single exam as an oral exam. And I couldn't write, but I could use a chalk because you don't need your wrist to write the chalkboard. So every single exam was a painful oral exam. Anyway, okay, here's the problem. A neutron with mass m, okay, so we have a neutron with mass mn, makes a head-on elastic collision with a nucleus of mass big M, which is initially at rest. Okay? And the question asks, how much kinetic energy does the neutron lose? What's that? It doesn't annihilate. No. It's elastic. How much kinetic energy does the neutron lose? Okay. So why does the neutron lose kinetic energy? Okay, well, it's an elastic collision, and there's conservation of kinetic energy. Is the nucleus going to have velocity after the collision? Yes, some small non-zero amount, which means it's going to have kinetic energy, which means some of that has to come from here, right? So what's our strategy in solving the problem? Before we just crank away at a bunch of complicated algebra, what's going to be our approach? Yellow shirt in the back, yes? Okay, and then? It's going to be messy, right? Because there's going to be quadratic terms there. All right. So we have the initial kinetic energy, 1/2 m(a) VA squared equals 1/2, so this is initial, m(a)(2) squared plus 1/2 mb vb squared, right, so we'll call this one b, and this one a, what I did in my notes, okay, and so this is kinetic energy, I just squared nothing with that, VA. Let's get VA2 squared, VB2. Okay? We also have momentum equation, MVA x equals MAVA2x plus MBVB2x, right? Because we can't necessarily assume that that the momentum is going to be all in x in the end, right? Maybe some y displacement there. Okay, so that's one equation, and we have a similar equation for y. MAVA2y plus MBVB2y. Is that right? A2y, B2y, and the initial y momentum is 0. All right?
Well, did the initial questions, or did the initial prompt say it was a head-on collision?
Yes. A neutron with mass makes, sorry?
Can't we ignore y as a head-on collision?
Can we? Or can you assume that?
Because it's a one-dimensional problem.
Mm-hmm. So you could have conservation of energy and still have recoil in y, right? Single momentum. Well, we could treat the magnitude of the velocity when it comes to kinetic energy, but momentum is specific in x or y, right? You had a comment? Why can you argue that there'll be no y momentum of either particle at the end?
Well, if it were a head-on collision, then the particles would only be traveling either in a positive or negative direction in one dimension.
Initially, right?
And I mean, even after the collision, if it is a truly head-on collision, then they'll either both continue one direction or the opposite direction.
I hear you saying that. I don't hear you arguing for why. Uh-huh.
So it's like two flat surfaces, it's like another two circles, but if you zoom in super far and just look at the point where they collide, there's no angle for the incoming object to reflect off of. So therefore, it would just be a single linear interaction instead of, the second dimension.
Okay, I like that argument. Anybody have another argument? People accept that argument?
Yeah.
Yes.
What about symmetry also? I think your argument is correct. What about symmetry? All right, these two things are not the same, so if there is deflection in y, one of them is going to go one way, the other is going to go the other way, right?
Yeah.
How do you choose that direction? There's no way to choose that direction. Yeah, but you can label your axes, right? But the universe does not prefer one direction or another. So unless there's some reason to choose a specific direction, like a slant or a deflection or an initial angle, then you're right. These guys are also going to be zero, right? So that simplifies that. Okay? Not even really part of our problem. Okay? Okay, so at this point we can, the easiest way to solve this problem is unfortunately to do a little bit of tricky algebra. You can write, and so it's an interesting problem for setup physics-wise, and that's really what you have to know, is that, let's think about what information we have here, right? We want the answer, we want the loss of kinetic energy expressed in terms of the masses, in terms of the masses of the problem, no. So to proceed from here is really just sort of algebra and clever substitutions. There's not really any more physics insight to be had, okay? But there is some, sometimes these problems are tricky because the math is tricky, and so you have to do tricks. You can churn through it stoically and get the right answer, but sometimes there are insights to be had. Okay, so we can express this one, we cancel out the halves, express this guy here as the difference in the kinetic energy initial and final, right? Because the kinetic energy lost by the neutron is going to be the same as kinetic energy gained by the nucleon, this big nucleus, right? Another way of saying how much energy is lost is saying how much does this one gain. And so that's, since it starts out with nothing, you could just express it like this. And so that's just VA initial squared minus VA final squared, right? Times MA. This is the same as MA times VAI minus VA, keep switching my ones and twos, times VA1 plus VA2, right? The difference of squares, I can express it in this way. And from this equation here, I have MB VB2, I can just drop the x's, is equal to MA times VA1 minus VA2, right? So here I have my two equations, and I can just divide these two equations, because you notice that then this term cancels this term, right? And I'm left with VB2 is equal to VA1 VA1 plus VA2. Okay? And then I can plug this in back here, right, or back into this one, and say M times VA1 plus VA2, so this is now MB, right, is MA times VA1 minus VA2. Right, so now I have these two equations. And so I can say that VA2 is MA minus MB, MA plus MB times VA1. So now I can relate the final velocity of the incoming neutron to its initial velocity just by the mass ratio, see? And this means that VB2 is 2 MA over MA plus MB, just by plugging it into here, right? Because I have VA1, VA2. All right? And that gives me, and from there, okay, we're out of time, but from there it's easy to calculate the final kinetic energy, right? It's just MB, 1/2 MBV squared. Okay? So it all starts just from setting up the equations. Okay, that's all we have time for today.